0404.
Let me confirm that date.
Yep.
Yep, 0404. Oops.
It's covering chapters 5 through 8, so you don't need chapter 9. Okay. At the end of today's class, I'll probably bring up the old exams, just kind of show you one or something, and we'll just kind of take a look and verify that we've covered everything and that you're ready to practice. In lab this week, you're welcome to work from home on Zoom for this week because we're doing practice tests. So if you have a place and a good internet connection and it's quiet, you want to do that, you're welcome to do that this week. Again, that's not the norm, but whatever. You're welcome to come in and just grind it out in here. Practice test, practice test, practice. Something I want to say about this before I forget. Usually I'll throw on about 2 questions from chapter 8 and 2 questions from chapter 6, maybe actually more. There's a lot of chapter 6 and chapter 8. There's a little bit of 5 and a little bit of 7. Now, to be clear, you can't do chapter 6 without chapter 5, and you can't do chapter 8 without chapter 7. So it's kind of, I don't know, but I'm just kind of letting you know, if you're really good at chapter 6 and 8, you'll probably be fine with the 5 and 7 that's required. Does that kind of make sense?
Yes.
So make sure you're good at chapter 6 and 8. All right. In particular, I've been looking at some old tests, and I find that I like to do, oftentimes I'll do 2 circular motion problems per test, 2 circular force problems. One with like a horizontal and one with a vertical. Okay. You'll see when you get to the practice test. In chapter 8, almost always I do a topic that has a plot of U versus X and then some word problem. So you'll see when we get started, there's the stuff that we covered last time in chapter 8, the kind of word problems with blocks, sliding, springs, stuff like that, swinging around. There's always one of those. And then there's always some kind of plot question or U versus X. That's the last piece that we're going to cover today. Okay. So without further ado, let's get into it. I'm going to give you the big picture. Okay. The last pieces are right. These are the 3 things we're going to cover today. It'll take us hopefully less than an hour and a half, hopefully about an hour and 15. Then we'll take our break and then we'll come back and just do extra practice the rest of the day. Fingers crossed. So I'll just tell you this. We know this already. Perhaps you know that work is equal to minus delta U, right? I want to emphasize this. This was the definition that we had last time. Well, if you recall, work had to do with an integral, right? So it turns out delta U can actually be, there's a minus sign, which is annoying. You're going to hear me say that a lot. We're going to restrict ourselves to one-dimensional problems for this type of work. And so if I'm trying to get U from f of x, I can do this integral. But watch out. Look carefully. This is not U. It's delta U. So we got to remember this is U final minus U initial. This is going to be U as a function of x. This is some constant usually. Usually, but not always, zero. And I'll explain more on that. It's sort of like a limit, right? If we go from initial here to final, sometimes when you plug in the initial limit, you get a 0, sometimes when you don't. You know what I'm talking about for calculus class? All right. That's the short version of that. Now we need to practice that. We'll take a guess. If you're trying to get f from u, well, let's think about this. To get u from f, I had to do an integral. What's the opposite of that?
Derivative.
Derivative. So that means, now I got to be careful. It's not just an integral, it's minus an integral. So then I need minus a derivative. I'm just going to leave it. So basically, I might give you some functions and make you do an integral or a derivative, and remember this minus sign. It's pretty hard to remember that minus sign, right? That's why. Sorry, I left my books here. Look on your exam equation sheets real quick. Find those equations somewhere. Do you see them? For me, they're like right down in here. Got them? I know it's going to seem stupid, but when you get a problem like this, check the exam equation sheet to make sure you don't forget whether you're supposed to do an integral or derivative, and remember the minus sign. Okay, piece of cake. But help me out here. Let's say I have some plot. And let's say this is, oh, let me make this color coded here. Let's say this is U in some units, joules. And over here we have X, meters. How would you get the force from the plot? What does this mean on a plot? Slope. Opposite the slope. So here, slope equals, slope is less than 0. So what should be true about the force? Got it?
So if it's a negative slope, it's a.
Exactly. Yeah. And that's why I'm going to be harping on this minus sign all day long, because it's easy to forget. And I'll give you an analogy for this later. Hey, we're done with chapter 8. Class dismissed. All right, all right. So now it's just practicing these things. Cool? Any questions about this while it's all up here? That's the summary today, too. In practice, there's a lot, you know how this physics is, right? In practice, there's always weird little tricks you got to remember and look at. So let's start with, I think we're on about, take a look at page 20 in your book. I'm going to do this example. And actually, I think I showed you a derivation there. Look at the top of page 20. That's me just showing you exactly what we just did. Notice at the top of page 20, I say u as a function of x is equal to some initial value minus this integral. So if you know a function for f of x, you just stick it in here, plug in the initial value of the energy, which is usually given in a problem statement, to do this. Let's do an example. Okay. Example. Let's say for a spring, it's minus kx. Okay. And I'm just going to do the integral from scratch here. Sorry. Just so you can see how this pops up. Okay. Delta U is equal to minus the integral f sub x dx. I'm going to go from some initial position, oops, some final position. And I guess I want to make this stand out, so I'm going to highlight this in a different color just to make sure that pops. Okay. In this case, on this side, I'm going to get u final minus u initial, that's delta u, is equal to minus the integral of minus kx. So those minus signs are going to cancel here. And I'll just go from x initial, x final. Hold this off for a second. Okay, in this case, you agree these two minus signs cancel? So I get u final. All right. Well, when I integrate this, that's 1/2 kx squared. Okay, I'm gonna see if this other red is working a little better. Okay. I'm gonna move this to the other side. Okay, so this would give us u final. Now, to be clear here, when we solve for u final, what we have really found is u as a function of x, or that's what I mean by u of x here. So in case you've been wondering, u of x means u as a function of x. Now, what does this x mean for a spring? How much it's stretched or compressed? If we set this to 0, that means the spring isn't stretched. If the spring isn't stretched, how much energy is in it? If you haven't stretched or compressed the spring, how much energy does that? Yeah, 0, right? So that's what I'm saying, like usually u initial goes to 0, not always. And so we see here, and we've been using this right before spring break, we used this. That's where we got the energy for a spring, right? Is everybody okay with that? All right. So now, what would be different in some other physics problem? Well, can you imagine on your test, what if I gave you a different equation for f sub x? You just stick it in, turn the crank, you're good to go, right? Okay. Now, let's do a quick example. Let's look at 8.22. All right. And I know it's going to seem too easy, but there's a few. I want to make sure we cover all the words that might appear on the test question. You know what I'm saying? Just so there's no, right? I know you could do this without me doing any more, but I'd rather speed up the process of doing your first example. So look at 8.22, right? I'm going to erase the board. Racing goes beyond Zoom there. Let's go into this whiteboard. Okay. think that's what it was, right? Before we get too far into this, a couple of things. Which of these terms is going to dominate when x is small? If x is a small number, which of these terms is going to be more important? This one. Think about it like this. 0.1 versus 0.1 cubed. What's 0.1 cubed? It's a lot smaller. See what I'm saying? So if you have small numbers for x, the first term matters more. If you have big numbers for x, the second term matters. So that's one thing I wanted to point out. Sort of like Taylor series, right? As you do more and more terms, you need more and more terms, right? Or if you want to be more and more accurate, you need more and more terms. All right. All right. Number two. But later on, because this is an algebraic problem, we're going to want to check our units, right? I need to know the units of each of these constants. Can somebody tell me the units of K? What are the units of force? What are the units of X? So what do the units have to be for K? Newtons over meter. Isn't it funny? This was in chapter 1 and you guys all skunked this problem on the test and now you're like, oh, that's so easy. I don't know. That's just how it goes, right? I wish it wasn't that way, but people are always like, oh, I should have got that one right. What are the units of B?
It's over meters cubed.
Yeah, you see it? I'm just mentioning that so that if we need to check our units later, we can. Good? All right. What are we supposed to do in part A? Determine the potential energy. Get U of X. Well, that's equal to U initial minus the integral of f sub x dx. Is everybody okay if I just write it that way? Just moving the U initial over. All right. Does this problem tell us what U initial is?
When x is at 0, use 0.
Okay, so if we go from 0 to x final, we're told in the problem, this is 0 if x initial equals 0. Is everybody okay with that? All right, race you, go. Wait a minute. Oh, it's, I almost screwed up the minus sign. Did you? Remember, there's a minus sign out front. There's a minus sign in front of both integrals, not a plus symbol. What's this one? Minus v over 4. In this case, typically when we're done with these problems, we change our upper limit from x final to just x. That way it looks right. We're just renaming the variable x final as x, just so the equation looks right. Because, right, basically what you're saying is if you go from 0 to some parameter, right, well, this would actually be a u as a function of x final, but there's no reason we can't just set x final to x. I don't like doing that in this stage for one reason, right? Technically, we don't want to have the same parameter inside the integrand and in the limits. That's a circular reference. That's not mathematically rigorous. So that's why I like to first do the x final and then at the end change it over. Hopefully this sounds familiar from separation of variables, right? All right, piece of cake. Everybody's good with this at this point? Looks like a normal spring, and then there's a small correction. Okay. Part B. At what position says u equals 0? Well, what should we do?
Set the US to 0.
Yeah, and I want to show you something here that might not be what you expect. I know this seems extremely obvious, but just trust me, it's worth talking about. Most of you, what would you do at this point? Move this to the other side, set them equal, cancel some squares, right? That's not the best strategy. We're going to go junior high on this. We're going to factor out some pieces, and I want to explain why. When I factor this out, can I factor out a 1/2 x squared?
Sure.
And I get what? K minus 1/2 b x squared. And here's the deal. By factoring, we can see either x equals 0 or, and now we get all of the correct answers. If we had moved them around, we would have missed out on this x equals 0 being an answer. And I've seen people forget that on test day, right? They don't look at the equation and say, well, look, x could equal 0. Clearly that's true from the top equation, but people forget to write that down because they didn't factor it for some reason. Also, this trick is going to be useful in chapter 9 and a few other spots throughout. Yeah, so sometimes it's good to factor because you remember there's two possibilities here. Whatever. And then out of this, what do I get? What's this one going to give me?
Plus or minus the square root of 2k over b.
And the plus or minus does make sense here, right? You could stretch this new modified spring to the right or to the left. So it's important that we include the plus or minus for this problem too. So just little things. You probably would have got all that, but does that make sense? Those are the question or no? Thinking? Oh, yeah. Just move this over, cross multiply by 2, divide by b, then square root. You get there. Maybe I'll do a couple of lines just to make sure. And maybe that's not what you're wondering about, but I'd rather. So my apologies. That was not, yeah, I don't know. Okay, I'm just erasing the other board, Zoomers. Give me a sec. What's part C say?
Suppose, or excuse me, determine the equilibrium positions.
Equilibrium positions. Okay, so this is the other thing that I want to make sure you understand for test day, right? What does equilibrium position mean?
When it's stretched out and no longer moving. When actually there's a better way to say that. When the restoration force is equal to the pulling force.
Okay, I want a general definition for equilibrium. And this is part C. We're looking for equilibrium positions, right? what does equilibrium mean? What is the dictionary definition of equilibrium? Force net equals
Zero.
So an easier way to do this is if there's only one force, as in this problem, there's only one force. So this is not that hard once you see it, but you are expected to know the following. It's relating to what you're saying, except there you were talking about two forces. In these problems where I give you some equation, we're looking at the net force already. So all you have to do is set it equal to 0. Right? So let's do that really quick. What was our equation for force? It was minus kx plus, was it bx cubed?
Yep.
We're going to set this equal to 0. What am I going to ask you to do? Factor.
I think you.
What's that?
Correct.
Oh, I caught it. Okay, yeah, sorry about that. Right? So we see two possible solutions. Either x equals 0. If you haven't stretched this new modified spring, of course it's in equilibrium. Otherwise, the two terms have to balance. So here, similar math would give us what? B over K,
It's K over
K over B. How could we check?
units.
And now we got our units. Remember that? Let's check our units. This is in newtons. Wait, that's not in newtons. This is a position. What's position units? Meters. What were the units for K?
It's over meters.
Newtons over meters. And the units for B were what? Newtons over meter cubed? Well, don't think. Just do it. Do a reciprocal. Units check. Good? Okay. And then the last part says, make some plots. Now, we're not going to do that. It says do it after class, but I want to read through, and there's one particular thing that I want you to watch out for. When I'm reading that question, it says, part D, suppose K equals 10 newtons per meter and B equals 5,000 newtons per meter cubed. Plot F versus X and U for values of X between -8 and +8 centimeters. What's going to be the issue if you try to make this plot? The numbers are easy. You can shove it into Excel. What do you have to watch out for? There's one subtlety. What was K? 10
Newtons over meter.
B?
Newtons over meters cubed.
And what was the range of values?
Centimeters.
Centimeters. You can't have meters and centimeters, right? So you're going to have to watch out for that. Did that make sense?
Yeah.
What am I going to do to you on test day? Mix up the units to see if you're paying attention, right? I love to say one number in meters and another number in centimeters and see if you actually read and remember to convert. Does that make sense? Not trying to, I guess I am trying to trick you, right? I'm straight up trying to trick you to see if you're paying attention, right? Because that's the kind of stuff that made that thing crash on Mars. Do you remember that? It made it all the way to Mars, and then somebody used inches and somebody used centimeters, and it failed. It's like a $3 million failure or something. Whatever. What units don't matter that much, do they? Okay, they do. All right, all right. Good on that. Just watch your units. Okay. 8.23 is there for one reason only. It's just to remind you of the following. Everything that we've been talking about here, and let me zoom full board here just so we've got it all. Let me do this here. Right? All this problem is making a big assumption. We were assuming at this stage right here, where I gave you this force equation, that this force was conservative. If you remember, what is a conservative force? At the very bottom of the page, I tell you that. It must be, the work done is path independent, and the work done on a closed path is 0. So basically, if you go from A to B, it doesn't matter whether you go up and down and then around in a circle and still end up at the same point. You should get the same amount of work, whether you go in curly Q's or just in the straight line. And if you go around and back, or up, then back, or around in a curly Q and up, down 6,000 times and then back, we better get 0 for the work. It's not a huge deal, but if you're a physics major, maybe you should pay attention to that. If you're a physics major, maybe you'd want to do problem 8.23. Otherwise, just know the bottom of the page. Got it? Typically on a test question, you are not going to have to prove any of this. I'll just say it's a conservative force. Do the math. Got it? Enough said on these? Feel pretty good on this, right? Thumbs up, thumbs down. Where you at on these? Feeling okay? You doing good? What do you think? Good? Okay, got it. All right, all right. Go to page 22 and read it while I erase the board. Okay? Page 22. So if you're good at calculus, usually you like this part of the class, right? Hopefully. At the end of the next problem that we do, I'm going to have a simulation that I show to try and make this more visual. Right now, it just feels like pure math. It's still going to be pure math for a bit. Good. Okay. Now we're going to review this one. Get F from U. And we talked about this already. Actually, I need to make this plot kind of big. And let me get my. Now the plot I'm going to draw isn't necessarily exactly the same as the one in the book. Just because this will be a little bit simple for me. Very similar, there's some ups and downs, etc. Okay, to be clear, this is a plot of U in some units. Maybe it's joules, maybe it's EV. This is X, meters, nanometers, some kind of units. We'll always have to be looking at those. So this curve is representing U as a function of X. It's a visual way to represent U as a function of X. We know you could get F sub X is equal to minus the derivative of U, which is equal to negative the slope. And maybe I'll put that minus sign in red to make it pop. If you forget this, It's on your equation sheet. You could find it there. This is the bad red marker. Okay. So let's kind of go through this here. Where is the force equal to 0? I'm going to run my finger. Tell me, say the word stop when I get to a spot where the force is 0. Do you agree? 0 slope, 0 force. If the force is 0, it's equilibrium. Do you agree? There's another one. What about over here? Yeah. All right. So now we're faced with these different types of equilibrium. This is something new that we haven't discussed yet. And actually, before I do that, let's do 2 more pieces. How about right here? What's true about the slope? Positive, negative, or 0? So what's true about the force? Okay. How about right here?
Positive slope.
So the force would be negative, right? It's kind of hard to visualize this, so I have something to help us visualize it.
Just like to draw imaginary tangent lines.
Yeah, you could do that. I'm going to do this. Right here. Doesn't this look vaguely familiar? Is that showing up, Alan?
Yeah,
Is the background too cluttered or is it good enough?
it's good enough. You can probably move it a little more to your right.
Is that better? I want this part to have a nice blue background right in here.
Yeah,
Is that good enough?
Are you trying to show the whole thing?
No, just this part right here.
All right, yeah, that's fine.
Does it get that?
Yeah, I guess it.
Believe it or not, this problem is nearly identical to those graphing problems that we have up on the board. Think about this. What's true about the slope here? Positive. What's the x component of the force on the ball? Negative. How about this spot? What's the slope right here? Negative. What's the x component of the force on the ball? How about right here? What's the x component of force on the ball? 0. This works. Now think about this. Just because the force is 0 doesn't mean the velocity is 0. Look at it. If I start this right here, we can see that just because the force is 0, the ball could still be moving. Remember, acceleration or 0 force means no, sorry, if the force is 0, the acceleration is 0, that means there's no change to the velocity. Good? So now, in this problem, do you agree the ball is not only moving left and right, but also up and down? That's where the analogy breaks down. But imagine if I had a really bright light and I was just looking at the shadow of the ball, we would see the shadow moving left, right only. Do you agree? So I want you to imagine, let's go back to this now. Five. Imagine there's a ball here. And we're not really caring about the actual up and down motion of the ball, only the right left motion of the ball. Or you could imagine, again, just imagine the motion of the shadow. If I take a ball, let's just get one here. Let's say I just place this thing from the equilibrium just slightly. What would the ball do? Kind of rock back and forth. On average, it's going to stay in the same spot. That's called stable equilibrium. If you could displace it a little bit, and it just kind of rocks back and forth, so basically any minimum, it's going to be stable. What if I put it right here? If I push it to the right, which way is it going to end up? Hella far that way. If I push it to the left, where's it going to go? Down here. This is unstable. Because it doesn't come back. If you displace it from the equilibrium, it doesn't come back. So essentially, concave up, stable. Concave down, unstable. Well, what's the concavity right here? Yeah, so it's not concave. So this is called neutral. In terms of, now to be clear, I mean unstable equilibrium, neutral equilibrium, or stable equilibrium. That's just the names. Every once in a while, I'll throw out a 1-point question on the test to see if you know this. Got it? So just make sure you look at that page the night before the test, whatever page this is, 22? Yeah.
I just came up with a really dumb way to memorize this.
Sure.
Think of it as like a bowl of cereal.
Yes.
Like if you try to tip it over, like is it, or like if you barely tip it over, is it going to come out?
Right.
Versus like where if it's upside down, like it's just going to come down because of gravity.
Exactly. Exactly. Yeah, that's totally true. If that works, I said go for it. Here's a fun one for you. Let's say I start this from right here and I tip it this way, right? Ever so slightly. Let's say it's just barely to the left. What's it going to do? What's the ball going to do? Then what? How far? To about the same height because energy is conserved. So something that people might forget about here is I know that kinetic initial plus potential initial plus any work from external or non-conservative. Check this out. I'm going to write this in a little bit different way. For this problem, we are only going to do this if it's a conservative problem. So what does that say about the work done by non-conservative? 0. And if you're saying, what about external? We're always going to do it so that this term is 0. I want to write this in another way, right? It turns out you could do an energy problem, except you could get the initial and final energies, potential energies, from the plot. You could get numbers from the plot for U initial and U final, in theory. Agreed? And then you could plug in 1/2 mv squareds. So this is another way to do energy problems. You can read the plot to get your U's. I want to go one step further. I'm going to move this K initial over to this side and this U final over to here. So I get minus U final plus U initial equals K final minus K initial. You agree? This is delta K, the change in kinetic energy. Look at this one. What's this going to be?
Negative delta U.
Negative delta U. Now, usually we write it like this. We just flip the sides. Think about this. If the potential energy decreases, delta U is negative, delta K is what? Positive. If you lose potential, you gain kinetic, and vice versa. So now look at this. Let's say you start with this bowling ball here from rest, or whatever this is, this pool ball from rest. What's its kinetic energy initial? 0. If it's ever so slightly misaligned, I'm going to lose some potential. Delta U is negative. The speed picks up. Where is the ball going to be moving fastest? At the bottom of the hill, when I've lost the largest amount of U. So it's going to go hella fast down here. Then it's going to come up here. At this point, my delta U is, what's delta U if I'm at the same elevation on the plot? 0. So what would be my change in kinetic energy? If I have no delta U, I have no delta K. So if I start from rest, I end from rest, go back and forth. Where is the pool ball going to spend the most time? At the highest part where it's moving the slowest, right? So this is what's weird about this problem. You spend almost no time at the bottom because you're moving really fast there. You spend a lot of time at the edges. Cool? This may not seem that special, but especially if you're in physics or electrical engineering or eventually chemistry and other stuff, or anybody that has to take quantum mechanics, all these things happen to relate a lot to that. Furthermore, we're going to use this stuff in physics 163 as well. So basically, you're going to do this graph again and again and again, probably in 162 and 163 a couple of times. All right. Let's see what else I forgot. There's a bullet sheet. Okay. Any questions about what we've got up there so far? Okay, I'm reading this. F is opposite the slope. When slope is 0, it's equilibrium. The equilibrium points are classified as stable, unstable, or neutral, depending on the concavity. Think about how the marble rolls. Oh, units. Oftentimes, we're going to use MeV and nanometers. So I haven't mentioned this yet. This is on your equation sheet, so you don't have to look it up. But 1 eV is 1.602 times 10 to the minus 19 joules. So 1 millielectron volt would be 10 to the minus 3 times 1 eV. It's 1.60. So it turns out in electronics, this is a common energy. It should be near the top if you're looking for it, top right. And then we've got your prefixes on the back, on the bottom. And I'm just being straight with you. Pretty much every year on a test, there's going to be some graph and the units are going to suck. And I'm going to see if you know how to use prefixes and units and stuff, okay? So I'm either going to use EVs and make you convert, or I'll use a lot of prefixes like nano, micro. And so you have to know how to use your prefixes for these problems. Finally, remember this. I'm going to say this one last time before we move on and do a practice problem. When I look at the ball moves up and down, right? But when we talk about the actual particle that's being represented here, it does not move up and down. It's just the shadow of the ball moving left and right. I pretty much every year ask this question. I say, does the particle, let's say the particle is released from rest. What direction will it move? Well, if I released a particle from rest here, which way would it move? Left. It does not go diagonally down. Right? The ball would, but remember the particle that we're representing is not the ball, it's the X component only of the ball. Does that make sense? So I'm going to literally ask you, does it move up, down, right, left, up and right, down and right, up and left, down and left? You know what I'm saying? And I'm looking for you to say right or left. Because that's the weird part about this. The ball really helps us understand, but it's only the X component that matches reality. Good? You know what I'm saying? All right. All right. Let's look at 8.24. Sorry. One last thing on 22, the last bullet point. In many real life situations, it's easier to create models for energy in a system. And then once you do that correctly, we can figure out the force. So some problems, it's easier to start with energy and go to force. It's used in quantum chemistry, quantum mechanics, and electrical engineering. So not everybody needs this, but everybody's going to learn it to pass the test. Okay, we're going to do 8.24. Go ahead and get rocking on that. I'm going to erase the board because I think I need 2 boards. 8.24. Any questions while it's up here? Okay. Let's do 8.24, then take our break. Okay. It's going to be 15 minutes or so. How y'all doing out there on Zoom? Any questions? Right. So Leonard Jones potential is what this is called. At the end of this problem, I'm going to show you a visual on this to try and make sense of it and make it cool. For right now, we're going to do the math, and it's going to feel a little bit weird. I've deliberately hidden some information in this problem so that we have to figure it out. So it's a learning problem. Okay, and that's the spelling. Kind of a funky spelling, but it's somebody's last name, I think. And it's a weird looking equation. 4 epsilon hopefully I'm not screwing that up. I'm going to double check one more time. That's right. Good. If you want to understand an algebraic problem, what's one of the first things you want to do? Understand the units. So to be clear here, we're told that sigma and epsilon and again, I'm going to show you the simulation at the end to make this make sense physically. All right. Sigma and epsilon are positive constants. So we need to understand the units. How would you attack this problem? This is a difficult unit problem. Where would you start?
Yeah, we do this. This could be wrong or feel like
Go ahead, try it.
not efficient. But what I would do is I would multiply 4 epsilon times this Q thing.
Oh, this is a sigma. This is okay. So this is sigma, and this is epsilon.
Multiply by epsilon and
It's epsilon.
set that thing just that.
Okay, that's a bad idea.
Okay.
Yeah, let's try something else. The term, just not that you couldn't maybe get there eventually. There's a much shorter way to get there. Good try there. Anybody else? Yeah.
Okay, so in order to isolate the variables, what we can do is set the potential or u as 0 and then divide both sides by 4
Yeah.
epsilon.
That's also, I think, well, I don't want to go that way.
Fair enough.
Okay, this is going to sound a little weird. When you add things, can you add apples to oranges? Like in math class, what do they say? Add apples to apples, oranges to oranges, right? Is there an addition here?
Yes,
What must be true if we're gonna do this?
those two must be the same units.
That's how you start. Does that make sense? You can only add apples to apples and oranges to oranges. Watch what happens when we do this. We're saying sigma x over 12, and actually let's do the units. The units of sigma x have to equal the units of sigma to the 6th. That's how you start. Because now, what does this tell us? I could cross multiply. Well, all right, let's do it. And you can stick the squares outside, inside, the 12s, whatever. Well, what does this tell me? What are the units of sigma? Meters. The sigma to the 6th would be meters to the 6th, so 6th root. Did that make any sense at all? Yes, no?
I think I would have done the same thing, except I would have applied it to also get this the epsilon as well.
Oh, we'll check this out.
Once we have that,
At this point, we know the units of sigma are meters. Sigma is some kind of distance. Well, once you know that, what's true about this term then? What's sigma over x? What are the units?
meters over meters.
Which is
One, I think or either was
no units. What are the units of u?
that's what I was going to compare it against. It was
It's energy. So what has to be the units of epsilon? So then you're done. Yeah, and maybe you were going to get there. I don't know.
it seems faster.
I think that's fast. So remember that cool trick. If you have two terms that are added together, they must have the same units. And that's what gets the job done in this case. Yes.
More or less, the approach I was going originally go for was going to result the same thing, like similar steps. Or
Yeah.
the way you did it is just shorter.
The problem is we don't know the units of epsilon and we can't figure them out unless we get the units of sigma
Yeah,
first.
that's what I meant. Like, so I could plug it back in to get
Yeah.
the epsilon.
I got you. Yeah. Yeah. Okay. Good.
Yeah.
All right.
Got it.
Now, I would like to erase this work so that I have room to do everything else. Is that okay?
Yeah.
So any questions before I do that? Okay. So that's how we got that. I'll try and leave that part up there at least. We got the units over there. All right, so now if we're going to do any more math, we can understand the units and do unit checks. That's important. Okay. So that was part A. Part B. B says get the force. What do I do?
Get u from you can get f from u
How?
by setting u equals to negative f.
Nice. U equals what?
Negative f.
No,
I did it backwards.
I need to do something to you.
Thank you, bro.
I need to do something to you. I need a derivative of u. Ready to go to work? Alan, let's circle around and see how awesome they are. All right, let's get to it. There's a couple of tricky steps. I'll come up every once in a while and show you some more. Let's crank this derivative out. Remember, the sooner we get this problem done, the sooner we go to break. For a lot of you, you're probably gonna like this too. Get this derivative. You can bring this x to the top, right? And it might make it easier to just kind of get your brain wrapped around it if you just make that x into a negative exponent. That's how I would start if you didn't notice that. Sorry about that. Okay. But maybe you don't need that. I don't know. For me, I like everything to be in the numerator when you're taking the derivative. Guys, feel right from the center where the subscript's too small usually. Good enough. All right. So it's not, but technically what you wrote is not mathematic. Squeeze that. Okay. That's fine. Yeah. Then you clean it up and factor some stuff out and make it look pretty again. And then check the units, right? At the very end. Yeah, something like that. Okay, and then clean it up, factor it out, check the units. Yeah. Good work. Sigma is a constant. So we don't, we just lay that sigma to 12 and 6 and 6 just lay around. Oh shoot, I forgot a 4 epsilon, didn't I? I'm a bad person. Do you see that? I forgot my 4 epsilon. I'll just stick it at the end. Or maybe I'll stick it out front.
Oh, I see.
See, I forgot my 4 epsilon. We would have caught that when we checked the units. So that's why you do that stupid stuff, right? There's 2 ways to write an epsilon if you're curious. There's the curly way and then there's the C with a line. They're both standard epsilon ways to write it. There you go. Yeah, because you did the same thing I just did, man. If we would have caught it eventually, you would have caught that, right? Yeah. Sigma is a constant. We're not taking the derivative of sigma. Taking the derivative with respect to x, right? It's going to change a little bit. Yeah, I wouldn't affect that with sigma and x. I would leave those inside. Kind of like the original. Look at the original form. See how it's sigma over x. Leave it. The reason you do that is because that's dimensionless. So you're right that you could have factored it out, and I wouldn't mark you down for it. But I think in practice, are you CS? Yeah. Right. It's nice to have a dimensionless parameter in your codes too, right? Because then you don't have to think about things like units. So because in this case you can get something that's close to dimensionless, I would leave the sigmas and the x inside. Okay. Yeah, something like that. So we got some 4. Is this multiplied?
Yes.
Or the 4 epsilon towards the end.
Yeah. I tend to.
Yeah, right? This is good. This is like 12, 4, 12, 4, 6.
I think I.
This is 6,
7. Wait,
yeah.
since that would be distributed inside,
Good, start working.
that would actually be, we read this. Oh yeah, I'm getting that towards the end. Since I don't want to skip any steps at the moment. Yep. So 4, 12, I mean, I could factor up the expo, but it's too much. Yeah. There's no point. 2 epsilon. Oh, don't read the F, tag the F next in front. Yeah. Brain fart because I was like overthinking. Originally, I was gonna do the cancerous way, so like, let me illustrate this. I was going to instead leave it as this. Let's not do that. And then afterwards, I was gonna drop it down like that, and then take the derivative. It was gonna be nutty. I did that.
You're still in that like. Higher order differential. Still not much.
I'm still on that. Calc 4 will do things too. Like, I think you saw the message that I sent where like we were like, bro, Calc 4 can't hurt you anymore. Yeah, that still gets me. Like I only borderline insane in that class.
Is that what you all got? Did you get it? Does that make sense? Take a look. It's minus the derivative, so minus this. Well, I just rewrote it, x to the minus 12, x to the minus 6. The derivative of that is that negative 12 comes down, lower the power by 1. Negative 6 comes down, lower the power by 1. So far, so good? Then what I chose to do was cancel this minus sign with these two that showed up. That's just my choice. Could you do it a different way? For sure. But now the 4 epsilon isn't negative because I canceled that minus sign. The 12 is positive. This term gives me this. And now I could factor out a 6. And in this case, let's check the units. What are the units of epsilon? Joules. A joule is equal to a Newton times a meter. Spring constant is Newton per meter. Energy is Newton times meters. Good? Yeah, they show up a lot, but yeah. Well, what are the units of this? Meters to the 12th over meters to the 13th minus meters to the 6th over meters to the 7th. Lo and behold, apples to apples. We get newtons. There's a 1 over meters, you get a newton. So there's newton per meter. There we go. Does that make sense for the unit check?
I see where I went wrong with that. I didn't do the math with the 4 epsilon.
Exactly. But you caught it? Yeah. All right, that's cool. What if I want to find the equilibrium positions? I think that's part C, isn't it? Equilibrium positions. Hang in there, we're almost a break. What are we supposed to do for an equilibrium position?
that force to 0.
Set F equals 0, solve for
Yes.
X in this case. Check this. We can speed up our lives a little bit. Do you agree if you set this to 0, the first term has to equal the second term? In this case, do a little cross multiply. You can do a little math there. So far, so good. All I did was I just said the first term has to equal the second term because I don't need to factor out here because X can't equal 0. Do you agree? It's in the denominator. So that's why I did this differently than the last one where we were factoring. Okay, no need to factor because X can't equal 0. We crank this out like this. All right. Look at page 23. There's 2 graphs. Which one is force? Okay, look at this. We know that the force equals 0 when X is 1.122 times sigma. If sigma is equal to 1, which it says it is in that problem, it says, oh, maybe I didn't say that. I think I forgot to say that. Part D, which graph represents force and which graph represents U if sigma equals 1 and epsilon equals 1, and we're ignoring the units to reduce clutter? Well, if sigma is equal to 1, it says the equilibrium is about 1.1. That means the force should be 0 when X equals 1.1. Which plot is the force? The bottom one. Look at the lower plot. You see the force equals 0 at 1.1 there? Pretty close to it anyways. 1.122.
This looks intentionally tricky. Just like pass by it. You don't really notice it.
Let's see what this means. Let's get to the simulation, take your break. If you want to, you could look at 8.25, but I'm going to talk about it on the screen with the simulation. So give me a minute. Hopefully I don't stab myself with this. You did it. You made it through that damn problem. Good work. So I missed this one. Nice work, everybody. That was painful, wasn't it? All right, all right.
The reason why it was painful because of
Well, Alan, what was it that you said in calc for, like something about differential order sequences? Something? Higher order differentials.
that's what it was.
Yeah, okay. Actually, I'm gonna make this just a little bit darker in here so I can see how I do better. I like to have some meaning for the problem, right? For me, it's so painful if you don't have a physical picture in your mind. You did all the hard work. Epsilon has to do with some amount of energy. You can see the constants labeled here. Let me do it with this light blue here, right? Look at this sigma, right? That has to do with the distance between the centers, right? So that's sigma. Notice that's the equilibrium distance. See how this is equilibrium right now? If the slope, oh, and let me label this. This is X, and this is U, right? we're doing a plot of U versus X, because that's what potential energy means. Distance is X, potential energy is U. So notice sigma represents the equilibrium distance between these two atoms. Okay, that's something. What does epsilon mean? We'll come back to that. It's some amount of energy. Now, right now, is this a stable or unstable equilibrium? How can you tell?
Okay.
Yep. Let me just label these again, just so it's a little more clear. Okay. So what's going to happen if I pull this and let go of it? It's stable. The molecule stays together. This is a stable molecule. Got it? Even if I stretch it a little bit farther. Now I'm going to do this slow-mo. Where does the atom spend the most time? Or sorry, where does the moving atom spend the most time? Close to the other atom or far away? Far away, right? High up on the potential energy curve. This is just like the marble rolling back and forth on the track, except the marble rolls up and down, whereas the atoms just move left, right. Everybody cool with that? What would happen if I bring this really far out? Approximately, what's true about the force? It's approximately 0. Now, it's not perfectly 0. Do you see it slowly moving there? So it's not quite a neutral equilibrium, but it's close. All right. And in fact, we could look at the forces. This shows the total force. Let me do this in slow-mo. Let me put this a little bit closer here. Let's do this in slow-mo. So the force is opposite the slope. And remember, the force is only in the XY direction. Oh, sorry, it's only in the X direction. Does everybody agree with that?
The way I see it is because this is one dimensional because we're only looking at the
X, correct.
X and the U isn't Y. It's just
Exactly. U is not Y. So this is not a trajectory plot.
Yeah.
Absolutely. Now, if you're curious or if you're a chem major, maybe you'd want to look at, you could compare what happens to the attractive versus the repulsive terms in the force. So this is, remember how we had one of these equations earlier where there was like negative kx plus bx cubed? The plus bx is the repulsive, the minus kx was the attractive. Only now it's these ugly Leonard-Jones calculations, all right? So far, so good. One last one. Let's say I grab this particle and put it right here and let go of it. What's going to happen?
depends on how it's programmed.
Okay, well, yeah. What were you saying? Yeah, let's watch it. Ready? It's just going to keep going. So what is epsilon? It's an amount of energy, right? It's the amount of energy required to break the atom apart. Cool. All right, so if we needed to, we could return the other atom now that we shattered it. So anyways, there's many other applications. This is just one. I thought you might find that kind of fun, good visual. The marble on a track is a pretty good analogy to me. All right, let's take that break. You've more than earned that. Sorry I took so long. Yeah.
Wasn't there like
Go ahead.
Isn't there a real life experiment where they shot electrons through a gold foil? It somewhat relates to this.
It's interesting that you bring that up. I actually have a poster of that right over here. You're thinking of Rutherford scattering. And what it was alpha particles, which were basically 2 protons and 2 neutrons, kind of like a helium nucleus.
Yeah.
And they shot that at the gold foil. And usually we discuss that the same kind of physics would apply, the same energy equations would apply, except we need to use electrical potential energy, which we haven't learned about yet. We learn about that in the next class.
Got it.
But it's in the workbook and everything. You got it.
Got it. Thank you.
Cool. So those of you on Zoom, let me stop the share here. And I just want to mention something to those of you on Zoom. Let me hit the lights really quick so I can see. And so if you're on Zoom, just give me a second before you take your break, if that's possible. And I think what we want to do. So for the last part of class, those of you out there on Zoom land, we were going to do 8.26, 27, 28, or 29, 32, or 33, or something basically. Just basically any problems from page 24 through 27. I'm going to put that in the chat. And then last. So obviously, if you are on Zoom and you want to just kind of do it all on your own, that's basically what we're doing, because I'm going to be circling the room a lot and I might not be talking to you that much. If you're from I guess if you're a student from some year other than this in the future, and that you're watching this video right now, I'll write this on the board for you. That way you can just stop the live stream and not watch the rest. So pages 24 through 27, practice problems. That's what we're doing in the last half of class, and I'm just going to be circling the room. So if you're in a future semester watching this video because you're out sick or something, just start doing that and turn off the live stream and practice. All right. Okay. Any questions from those of you on Zoom? All right, right on. So then in the last half hour, it's good to set the time. Take a short break so we know today. Let's see.
Oh, you know what it is? Do you do a lot of pulling? Mostly. I do a lot of pulling. I do a lot of presses.
Okay. Yeah. Pressing it kind of big.
Yeah, it does. It's my skin.
All right, let's go ahead and get into it. Just really quick. The rest of the class, we're just gonna be doing practice problems, all right? The last 10 minutes, I'm gonna bring up a practice test and we'll just go through it. So I recommend starting with 8.26, and then after that, you can do whatever you want. You can do 27 or 28. It's critical that you do some of these problems, right? Because then you can do the practice test. And they kind of are all showing you variations on what's going to be on the test, right? There's going to be some plot on the test. I'm not lying to you. It's just going to be there. So if you want to see the 8.26 is kind of the last one to help you kind of work your way around. It's got some of the units finally, etc. And then there were some that I kind of liked. I like 29, 32, and 33 were also good. There are those kind of problems, word problems. And then next time, we're going to start up with chapter 9. Okay. So let's just get to work, talk as much as you want, take as many breaks as you want, goof off as much as you want, whatever you got to do. Just, yeah, let's have a good time and try and do a couple of problems. All right. See if you can at least get 26 done and maybe start another one. But I'll be coming around. Alan's going to loop around. We'll check in with you on Zoom as periodically if you need it. So those of you on Zoom, hopefully you can see my message that I sent to the chat. If you took off for your break before I got that to you, sorry about that. So yeah, if you want to just tune out and then come back at the last 10 minutes, that's cool too. If you want to turn off your Zoom and rejoin at the last 10 minutes, that's fine too. Just problems and solutions and practice. Let's do it. All right. Yeah. Oh, I did? Oh, on the video, you mean? Up on the board? Oh, yeah, it's obviously 2.6. Sorry about that. Yeah, thank you for letting me know. I'll put that in the live stream in the chat. I'll have to do that at the end. Okay, thanks for letting me know. If you have it in your notes, you may go back and correct it. Peter was saying I accidentally wrote 2 to the 1/2 on the board when I should have written 2 to the 1/6. Sorry about that. Good. Thanks, man. What do you think? Got some ideas? Okay. Okay. If you've already got it done, you can always, you know. I don't know what I can finish it. What do you think? You doing all right?
As for me, it's been taking 50 derivative for the equation?
Yep, yep,
Okay.
sure, sounds great.
Thank you.
Setting the U zero with stable.
That's gonna go 0.
Zero, which exact, this is, but I know there's. So let's see the exacts. It should be. Interesting. I want to make sure. Yeah. So, all equal, that's what.
Oh, hey, I haven't seen these points in a while. We just do part C, where we determine the force at each point.
Yeah, don't worry about that. So it's not-
First.
Write those things down.
Yeah, yes, this is your first day, right?
At least I
You should
thought
be
it was.
transferring some of this.
All I know is like. Values and truths. Right now, it's
So all of that
I think this
stuff.
one,
right,
I
you
just
might
want to
want
see.
to see your own kind of cheat sheet, because you really can't use it on the test, you have to kind of
Okay, I
summarize
did
this
this
track
right.
and know.
So it's moving to the left. 42. This statement right here. Okay, well, 0, that's gonna be 0. Well, it's just.
To get problems done, you kind of have to have this in your mind, in your own way.
Oh my God, I wish I didn't see like that.
Got this to work. Kind of what you need to supplement.
Yeah, you could be right. Yeah.
This one looks like it, so it's very.
Okay, yeah.
When you factor out this.
Right, so this is where we do, yeah.
In order
Or differentiate, whatever. So for you.
Instead of having the physics problem, right, like.
Or in other words, it's just equal to joules. I'll just use joules. I'm just gonna ignore the,
So now we're not doing that because we want to focus on other parts, but these should have meanings.
let's just ignore the coefficients or the constant coefficients in
Keep
front of
that in
it.
mind.
That's not gonna matter, so if I just clear this.
I kind of just ignored the units. It's kind of.
Oh, that's kind of
went
it.
to the, just to whatever I put.
So I'll just.
So this negative is,
So part two.
not next to the right, so you can distribute the negative.
So you can distribute to each basically.
So this would be negative. So these other,
Yeah.
so you can do
Fall asleep. I get it.
All right.
Indications.
No, it's just
But,
the second time I give this lecture, it's like. Yeah.
then now.
All right, I'll let you work.
Yeah.
Okay.
Or some whatever.
What do you think?
coefficient.
You all right? Making
Yeah.
good way? Here's the tricky thing. Do you see any units on those numbers in the project? Yeah, so now you write hidden somewhere in there, you have to know that anytime you finish for X, you gotta get the nanometers on it, test that.
So for that's very cool. It's 10 years.
Basically, I want you, if I start plugging in numbers, those numbers in theory have units implied on them. Just like the units of alpha or K or B, there are units on them implied. Those numbers also. There's gonna be some units associated with it.
To everything.
In order to make these equations fit easily on the page, we end up doing this a lot where we ignore the units or something, right? And then at your final answers, you gotta learn to put back on. Cool. What's that? So basically, look, right here, what I would say is, when you take the square root of this, what do you get? Okay, so that would be 1.58 nanometers. See what I'm saying? Yeah, so your final answer, just slap a nanometers on it, so that it is. I didn't write the units on it. I'm assuming you know that you have to write if your final answer is no. Does that make sense? Yeah. It's kind of like a brutal thing your instructor does to you, but every physics book kind of does that. Cool. Always be thinking about units. How about you? All right. How do you find the equilibrium points? No. Equilibrium means what is zero? And F is not U. You gotta take the. How do you get from U to F? Yeah, the negative derivative. So if you want to set something to zero, first take the negative derivative to get F. Remember that on test day, don't screw that up. Got it? People do this all the time. They see the U, they grab it, they set it to zero, but that just gets you points where the energy is zero, not. Look at the plot as well, right? Look at the plot. Can you tell where the equilibrium points are? Where the slope is zero. This one, got it. Okay, is that good for now? All right, cool. How about up here? How do you do? Yeah, yeah. What is the unit I said on this plot? What's that? One sentence of whole. Label the axis. Second, let me get her quick.
Yeah.
No, no. Oh, it's vertical versus horizontal. So U is. So that's not fair. I would say that U parentheses. So the thing that you're plotting is U, the units are even. How did you get the force? Minus the slope. What are the units of the slope? Is that a Newton? These are lowercase. Okay, so EV power. Right. And so what happens is, very few times do I specify what physics you have to write your answer in. This is one of those times where I say you must write your answer in that. What about you? Doing all right? Okay, that makes sense for you as well. Okay. So I should go away? Yeah, I'll come back. How you doing? Getting there?
Yeah.
Is that the part you were working on as well?
Yeah, but I would just be, my mind is just scrambled eggs at the moment.
That's fine.
Class, but I'm
So you
getting
could-
the gist of it.
You can do a railroad track to figure out how to get to newtons.
Yeah, correct.
So like you do, how many EVs per joule, meters, et cetera, per nanometer, something like that. Okay.
I'm just converting the.
Yeah, exactly. Trying to figure out the units.
Yeah.
Just, right, if you agree it's EV per nanometer. Well, let me say this, way. Force relates to slope, right?
Oh, no,
You agree the units of slope are going to be units of rise over units of run? What are the units of the up and down?
Up and down in U, right? C and joules,
No, look.
or EV.
Yeah, so that's EV, not joules. And then this one is X. So X is the area. Okay. So now, what are the units associated with this? It's the units of the slope, right? So you could write this as equals to rise over the slope. Yeah, which is E degrees. EV is supposed to be capitalized. It's weird. It turns out it's capital E.
Well, technically, correct with this.
Could you do a railroad track to get that dimensions?
Yeah.
Again, on test day, usually this is like one of the few questions where I specify, you must answer in newtons to see if you know how to convert. If you need that conversion factor, I think it's on your test equation sheet. Nanometers, I think you got the prefix chart. Got it? Cool. Oh, wait, you said you had a question.
Oh, yeah.
Sorry, I forgot.
The question was, that's just,
Yeah, that's it. Equilibrium position.
there's something. I was asking. Something that didn't. Questions. I mean, or I could have gone past those pretty much.
Oh, this.
Like, this-
And then you just write the units.
Pretty much. Well, it's right. I know you realize like what that.
Right. That's what I'm trying, this is why we're doing it, right? Because there's a bunch of stupid little things. that you can do with practice.
This is actually really important. It's just. So easy.
Yeah, but I mean, let's face it, a few times, there's times when it's for plus and minus.
Yeah, definitely.
It's advantageous to write your parameters in your codes as dimension, so that's why. This is a good idea. Signal with X is a good idea. So trying to make everything dimensions parameters is great.
Actually, I just pretend they don't exist. And then I just go back and how to get them back.
What I like
So, right at the end, I just finish the problem and I go back to these students. So, go back to you.
Now, my cards, right?
Oh, that's not, can't you just.
Maybe not making it as efficient, maybe not making it elegant. We don't like to make it work, code and model, because that's what we're constantly doing, is trying to model reality. So the kinds of techniques that we think about in physics, they.
Well, they do. I've noticed that a lot of the problems with these, I would do probably do like the problem. I think, for example, for the spider.
Yeah, how it might behave, like, let's say we were doing CGI, right? It's simple things, right? And sometimes it's actually easier to have physics in it, right?
Yeah.
Because then you just set the initial condition and say, what reality is Right? And then the animation. Should I go on? Did I get that question? Yeah, just plug them in to your force equation, make a table, draw the dots, see what the curve looks like, check and see if you got it right. Yeah, you can literally draw them, right? So yeah, if you plot these, you can then plot this. Is that good? Now this is you. This is you. You're gonna make the F plot. Hopefully you can kind of think about, oh, does this kind of make sense or not? Like here. should the force be
I'm just
positive or
confused
negative?
because like it's asking for the U versus X.
Large or small?
I don't know, I feel like I should go with F of X instead.
Right, so you can kind of tell it's across zero right about there, right?
Yeah, use it
How about here?
Yeah,
Force
that's
is
what I was lost.
large or small? It's probably gonna go like this. See what I'm saying? And then you can kind of, okay, just make the plot, draw the curve, see if it kind of makes sense. Is that good? We aren't always gonna do that, but I feel like once you can see it's gonna do that. That will kind of make sense now. All right, so you know what it's gonna be. See if your plot kind of looks like the.
So I say just do it force, right? Because I mean, you already have U versus X.
Yeah.
Try to do it force for now, so you're not wasting any time.
Fair enough. That's my battle plan.
Speed.
Oh, for sure. I got it.
Or have you checked the solutions?
I have.
Or-
It was F. Like I had to look at the solution just
Yes,
just
that's it.
just to be safe about it.
There's no shame.
I guess you can.
Solve a bit of a guilty pleasure sometimes. In case if I ever do catch some shit. Hulu, that is.
So, yeah. If we want to get here, it's here.
Alright, HP Lovecraft is weird. HP Lovecraft is weird. What if you do not Google HP Lovecraft's cat? Why should I? Fair enough, I did call it out. Screw it. I don't know. Say HP Lovecraft. It's such a stupid meme. But like it's actually true though. That was actually this cat's name.
So the guy that was his
I know this was in the early 1900s.
All right.
Yeah. Excited, right?
I'm going here.
Yeah, for sure.
Which one? Yeah.
Yeah.
Okay. So how's that?
So the X, so stay 9 meters to the force equation for the force. P so there's still B.
Yeah, it seems crazy, right? I did tell you how to do this earlier in the day, but I said it like that.
I think it would be
Many things we did.
Yeah, EV.
You're trying to get speed. How are you gonna
Just
get speed?
because you use this information.
Yeah, I'm trying to convert the ES for you. Get that into the tool.
I would say inversely, because inversely implies one over, but I think I know. Yes, if one increase, it would decrease it. So. Yes, yes, that, right?
It's like,
Do you agree that's basically what it started? You get the U's kind of flop. The K's bounce off the ones that be. So look, you start with the marble here. You want to get over there. You're gonna run into trouble. At the top of the hill. What's speed? Fix the top of the hill. Go ahead and say what you got. It's okay, it's okay, right, this is your first day learning this, and I did not instruct you at all, so I was just curious to see. Right? If you're trying to get the U's here, you know the trouble spot is here. How fast do you need to be moving? Super fast?
So the only thing I've
Fast?
seen is that
Very slow? As long as you make it there, it's just now bigger than zero, you have to keep going and make it.
energy.
So speed to zero.
Oh,
Bigger than
yeah,
other
I think
numbers.
because I couldn't understand why you
Style.
EV over now.
Then give you some ideas.
Yeah,
Yeah, it's crazy, right? I didn't tell you that at all. I scared them. Does that give you an idea how to approach it? Okay, so then what you're gonna do is, you probably get stuck, check the solutions, and then when you do some of these other ones.
So then instead of
hopefully you
EV,
do without
it's gonna be
Got it?
or EV over there.
Alright. I think I did a lot of description. of solution. How about you? Alright. Well, you're up.
So then would this be counter ignition?
Getting there?
Yeah.
Making your plot?
No, what I was confused about was, this was the same sketch. Oh, wait, no, never mind. I was
Yeah.
looking at it. This is part F, isn't it? It's just the other
Part
side.
after is something totally different.
Oh, okay, I see what you now. I was tripping up about that. Other than that, I got part E.
Okay,
I
okay.
do better.
When does this class end? 45?
Yep.
Okay, okay, I'm gonna start getting the test ready. You guys go ahead and keep working.
This is what I got.
Isn't that fun? I don't know why, it just takes me time. I just love, I don't know. Ball on the track.
Just satisfying.
Oh, are you gonna get the lab assignment back?
Actually, I didn't get all of the lab assignments until today, because the secretary took them home last. Yeah, so anyways, I've got them graded. Everybody got an 8, 9, or a 10 for the most part. I think there was 1, 7. I'll get them back to you next time, because I haven't typed in the scores yet, because like I said, I just finished that a few minutes ago, a few minutes before class. But you did pretty well. All right. All right. Pretty much everybody got a good grade. I felt sorry for you guys. Oh man, I was so angry when I got here and there was no labs. I'm like, what are these students doing? And then I'm like, oh, whoops, the door was locked. They fixed that. It was supposed to be open. There's classes in this building on Friday. I don't know why they have the building locked, but they've promised me that will not happen again.
Yeah, I had to call campus police about that.
Yeah, so I feel bad that you guys got screwed over like that, so. Yeah, whatever. It's not supposed to happen, and they told me it won't happen in the future, but
Yeah.
what are you gonna do? All right, all right. Hey, everybody, give me your attention real quick up here. I know you could keep working on this problem, but I know you got the solutions and you can do it at home. So give me your attention really quick. I don't think I put any Excel calculations on this test. It's coming for you next Monday. Newton's laws, you got the work and energy, right? We've talked about this a lot. And then don't forget, I probably should put these together there. This is also chapter 7 down here. So you know where this is, where the practice tests are. Look at all these energy problem tricks, right? There's a whole bunch of tricks. Or I guess these are just all kinds of tricks. Here's what we've been doing today. So rather than just talk about this, you know what you got to do. Let's actually look at an old test and see if you recognize these problems. Okay. Here's a problem. You got some blocks, they're being pushed. We're talking about force. Friction is negligible. So we're talking chapter 5, right? Forces. This looks like talking about Newton's second law or Newton's third law, something like that. There's another one. Gee, isn't this exactly the same problem that was in the workbook? I gave it on the test and people had trouble, so that's why I put it in the workbook. This question is pretty much on every single test, every single midterm 2 that I've ever given, and somehow people still miss it. Everybody wants to say normal force and weight are an action-reaction pair. Don't screw this up. I make it worth 2 and just get angry when you screw it up and you lose 2 points, all right? All right, let's look at this one. What type of problem does this look like? I'll give you a second to read it. You got a block on a level floor. The block compresses a spring, distance x. What minimum spring constant for it to move upon release from rest? And assume our spring constant is that. How far does the block travel? So when I think about the block traveling, what type of problem does that look like? Energy, K initial plus U spring plus, is there going to be work done in this problem? Friction. So you'd have to get the work done by friction, all right? So that's kind of how you do a chapter 8 with a little bit of work, which was chapter 7. Okay. Oops. We know how to do that. So the first one, when you're talking about this, what minimum spring constant is required for the block to move, what might you do for that one? The K has to, the KX from the spring force has to overcome the mu static N. Yeah, so an FBD. All right. Oh my gosh. You got U equals some ugly looking thing here, right? What are the units? Figure out the force, list the equilibrium. And then notice this part. The particle starts with this speed and starts moving. This is the kind of question where you do K initial. Oops. Plus U initial equals K final plus U final. You know what I'm saying there? Obviously, this is what we were doing today. Okay, let's clear that. Let's keep going.
I have a question. Are you going to include the ones that have some work or like on the test? Like for example, okay.
So it just depends on the year and what yeah. So every year is a little different. I've never given the same test twice. So sometimes there's work done by friction. Sometimes there's not. You have to be ready for it.
Okay.
Got it?
Got it.
Okay. Let's go to this one. Okay. All right. Whatever. This looks like an FBD problem to me, right? You got some blocks. They're in touching. What force is holding up block M? Friction. What force is making block M go down the ramp? No. The rocket is making 3M go down. What force is pushing M? What's that?
3M.
Okay, so a normal force between 3 and 1. What else? mg sine theta, part of gravity, right? All right, I'll let you guys try it later. Ah, look at those units. Got it?
Are they in the back as well,
What's that?
those units?
Yeah. Well, nanometer, that's just a prefix.
Yeah.
That's on the back. EV, that's on the back on the far right. Okay. Oh, this looks like a problem I assigned you guys. Let's take a look at another one. How might I mix this up? Well, I probably won't do Excel this year. It's like I said. Some blocks. This one I gave you some numbers. Do you see that? So sometimes I'll give you numbers, sometimes I won't. Oh. Oh, look at this one. Here I give you a number for the angle and the coefficients, so you could plug in those numbers, but your final answer has to be 3 sig figs times mg. That's a very common way I ask you to do problems. Forces. Oh, yeah, EV in nanometers. You guys love it, I'm sure. Right? Here I give you a mass. I tell you some stuff. It looks a lot like, notice this question. What minimum initial speed is required? Wasn't that like what problem you were just looking at? 20, what were we doing? 26 part F?
Yes.
So this is a comment, right? Here's the force. Look at this. Look at this. Answer in newtons. So I give it to you in EV. So basically I'm requiring you to do the conversions. Oh, this one looks kind of familiar, right? It looks like they all look the same to me, right? Speed of the block as it passes over the top of the hill. How are you going to do that? Circular motion, what? What are we, forces, energy. What's that right here? What's, yeah, would you try and do energy or would you try and do forces or what? You could do forces, right? Normal force, mg, mac. You guys screwed that up on your labs. Remember that? You said T equals mg. You forgot about mac. Oops, AC. So watch out for that. Initial height, that's going to be an energy problem, right? Have you seen this where there's a circular motion FBD and then an energy problem and you do both and then you solve for something? It looks a lot like, look at question 8.29 in the workbook, page 20. They're all the frickin' same. So if you do the practice, you're going to rock this. Right? If you don't do the practice, you're going to be terrible. There's just, that's the problem with physics. If you don't practice enough, look at this. This looks easy.
This looks like we did, except it's not,
Yeah, there's basically the same problems. And what I do is I mix it up. I say solve for a different variable, or I give you something else, right?
a slight difference in our.
Yeah. Okay. I love this. This is basically a really, really hard problem. So I try to warn you if it's going to be like that. All right. Power. Here's one that has power output, right? Ah, this is great. Look at this. Spaceship was carrying evidence of steroids by the curling team sent to Korea. You guys remember that scandal a couple years ago?
Yeah.
The Korean curling team was doping.
Oh, we love the good old
Or no, the
HGH.
Russian. Yeah, whatever. Anyways, it's kind of funny. Oh, here's a fun one. Some Newton's laws. I'm telling you, positive, negative. Oh, look, there it is again. Mg and M are not action-reaction pairs. All right. Is that enough for tonight? You want to see one more or not?